Hello. Today we're going to talk about pure functions. What is functional purity and why is it beneficial for us? So how do we define what is a pure function? And essentially, a pure function must always return the same value given the same inputs and do not do anything else. So that means no printing to console, no writing to the files, no playing sounds, you get the idea. And I guess the easiest way to look at it is through examples. So here are some examples of the pure functions. So this is a pure function because it's basically just adding two numbers together. So you have this, and if you give it 2 and 2, 2 plus 2 will always be 4. So it is a pure function. This is also a pure function despite it having some mutability inside of it, but it is a pure function because if you give it a string and you give it the number of times to repeat that string for the same parameters, the result will always be the same. Random number generation can also be a pure function. So if you have a purely functional number generator, you have this random number generator thing, which is the initial state, and then you do some math, and then you return a new random number generator along with a random number that you have just generated. And this is a pure function, given that you give RNG, which is, let's say, the seed is 1, you will always get the same number because it's just math. And it is actually how most random number generators work. Your system random works in a similar fashion. It just mutates the random number generator in place and starts with a seed which is probably dependent from time. But essentially it's the same thing. So all three of these are pure functions. And these are not pure functions. So this function isn't pure because, well, first of all, we give it 0 arguments. So if you give it 0 arguments, it should be a value because, if there's no arguments, the result should always be the same. But it is not the same because every time we invoke this, we go and do a side effect, which is we increase this counter, which is defined here, and then we return the value from it. So every time you invoke this, even though the input arguments are the same, the output will change, and that makes the function impure. Same here. In this case, even though the return is void, which means nothing, so you can give it the same input, and it will return the same output, which is nothing. It is impure because it will do a side effect, which is it will print to the console. It will do something besides returning an output. Another impure example is prompt, which is also, this kind of combines the both. So it can return a totally different string for the same question because you read that from the user input, but it also does two side effects here and here. So all of three of these are not pure or impure functions. And even this is an impure function because even though it satisfies this, the output is dependent on the input thing, it still has a side effect because sometimes it does not return an integer for you. Sometimes it stops the execution with a side effect of throwing an exception. So exceptions also make functions impure. So why do these pure functions matter? When we write programs, we very often have to basically, our problems are structured in such a way that first we have to do some computation to know what to do, and the code that computes these are basically just pure computations, and they can be implemented and called pure functions. And then we do some actions based on those computations. So these are called effects or effectful functions. So first you compute what you do, you make a plan, and then you execute that plan, and you by executing the plan, some effects happen. And when we do not strive for functional purity, when we just write our code willy-nilly, it is very easy to write programs that intermix those two stages. So intermix computation and effects. And then it results in a code that is kind of hard to follow and hard to test and other things. So let's take a look at an example. So a very simple, like a menu program where we just basically sit in a loop until somebody tells us to exit. And then we say, please enter your order. And then we read the line and see, if somebody enter 1, you do something. If somebody enter exit, you just drop out of the loop. And otherwise you say a non option. And this is straightforward. But at the same time, it does intermix what you want to do. So there's a couple of concerns here. So one concern is, taking this and turning it into whether it is a valid option or not. And other concerns are the side effects of doing things. So we can try to rewrite that into a more purely functional style. We do that by extracting these parts. So first we define an enumeration choice, which basically states what our choices are. So we have the choice number 1, and we also can exit the program. And then we have this pure function called parse, which takes any string and then turns that into a choice. But if the string is invalid, we don't have a choice, and therefore this is optional. And then we can split this into another impure function, but still a separate function called ask, which actually asks the user to enter his order. And then the menu looks like this. So we start with no choice, and then we go until the choice isn't exit, and then we ask, we try to parse that, and then depending on the choice, we do something. So even though there is slightly more code, there are significant benefits to this. So as I mentioned, there's a choice type which clearly lists what are the possible choices, and you can even attach documentation on top of it, and you can reuse that type throughout your code base. And it's very clear when you look at that type, like what are the options, and you don't have to kind of extract that from the previous big menu method, which was very intermixed. The parse method that we wrote is an easily testable pure function, so you can very easily write tests for it, whereas previously it was hard to write tests for the menu function. If we provide the ask function as a parameter, we can even make the menu function testable. And each function kind of does a single well-defined job that is easy to write documentation for, it's easy to test, and the menu function is the most complex one because it just takes all of these things and combines them, connects them together, sort of like a controller function. So what are the other benefits? Pure functions also allow equational reasoning. They are simpler to understand, they are testing friendly, caching friendly, multi-threading friendly. Let's go into details of each of these. So what does allows equational reasoning mean? An equational reasoning is the capability to think about the code as if it was a mathematical equation. So everybody who's a programmer probably studied some sort of math, in school or university. And in math, the left and right sides of the expression they are interchangeable. So if you say a equals 5, that means 5 equals a, and vice versa. So if we have an expression like this, let's say x plus 5 equals y, and 2x minus 5 also equals y, we can basically solve this equation pair by doing these things, by moving things around. Here we just do x equals y minus 5, which is you take this and you move that to the right side and change the sign. And then you can express, well, what is y? Well, we already have this, but we just flip the sides and we say y equals this. And then we can take this y and interchange it here. And we can say x now equals this thing, which is composed of y and also this part. And then you do some substitutions and according to the mathematical rules, and you figure out that, hey, x is 10. And then when you know x is 10, you can put that into this equation, right? And you say, you can put x is 10 here, and you say, then y is, you do the math and you figure out that y is 15. So basically you move the data back and forth here. And when you program with pure functions, same rules apply. So if you have this compute function, which is pure, right? You can say result 1 is compute plus compute, and it will be 6. And you can also say, do not do that function twice, but do it once and store that into a variable, and then you can just add these two variables together, and result 1 and result 2 will be the same. However, when the functions are side effectful, when they aren't pure, this equational reasoning, it breaks down, because if you have this compute and you do a side effect here, then if you invoke this function twice, then this counter will be increased twice, and you will have a different result than if you just invoke it once and then do this addition on x twice. So this and this becomes not equal, because the compute function is not pure. And why does it matter? Essentially it matters because when refactoring code later down the line, it is incredibly freeing to be able to move the code around without worrying that changing the position or extracting the code or doing any other kind of transformation up on the code will break the code and will change the actual result. Also, when debugging, it also comes in handy that you can change the code according to the equational rules without breaking it, to make it easier to debug, to put it in whatever shape or form you need for the debugging process to go easy. And code that is expressed with pure functions, usually they form clear expression trees. So kind of this is made from that and that is made from that, instead of having a lot of state and mutations. And the code is more about inputs and outputs, instead of we have some state and then that changes over time, which is kind of complex for the human brain to understand. So when you think about it, and if you've ever seen what Unreal Engine blueprints are, the code kind of becomes like that. You have this node, which is a function, and you have some inputs and you have some outputs, and it just kind of flows inwards and outwards. Okay, so let's talk about how pure functions make the code simpler to understand. And basically, they do that because with pure functions, you only have two things to worry about. It's inputs. So the inputs can be, either the function parameters that come to the function, or we can also access values from the class or struct scope. And the output that the function produces. And what this does is it makes the code local. You don't have to worry about where the values come from or where they are going to be used. You just don't care about that. You know that you're going to get some data, you're going to do your own thing, and then you're going to return it, and that's it. Pure functions are also testing friendly. So, you just pass in the parameters and check the output. It's very easy. So if I have to write a test for a function, it's like the easiest thing ever. I just give the parameters and then I say, okay, the results should be this. Because pure functions do not do anything except for producing output, they are very easy to cache. So maybe we have some very expensive function that does some very intense calculations here, and if we want to cache that, it's very easy. You just use a library method called memo, and basically it memoizes, it caches it, and so on the first invocation it will do the computation, but on the second invocation we already have the result, and because we know that for the same arguments we will get the same results, we don't need to invoke this expensive function anymore. We just can get it from the cache and return it. And of course, for the different arguments, that will result in calling the function again. Pure functions are also multi-threading friendly. So because they do not share any data, or if they share data, they share only mutable data, they can be run in parallel easily without worrying any deadlocks or data corruption or race conditions, which are prevalent in multi-threading programming. And although Unity games are often single-threaded, it still comes in handy when we want to optimize some specific piece of code to use all of the CPU cores. And in these specific situations, you might get more performance out of purely functional code just because it can use all of the CPUs instead of using imperative code, which relies on state mutation but cannot be shared between different code without expensive locks. So with all that, let's define some architectural guidelines for our code to follow. Essentially, pure functions should never call effectful functions, because when you call an effectful function from a pure function, the pure function loses its purity. It becomes an effectful function itself. Meanwhile, the other way around, the effectful functions are free to call either pure or effectful functions. So the effectful function can do anything. And the effectful functions should basically be invoked near the program entry points, such as an update function from Unity or mouse click callback or some other entry point. And this helps to make sure that these effectful functions only invoke pure functions and not vice versa. So the layer is kind of, you have your entry point, then you have your effectful functions, and down the line then you have all of these pure functions. And preferably, most of your code should be made out of pure functions, not effectful functions. So most of your code should do the calculations, and then after all, you apply those calculations. So let's take a look at how this might look in a simple example from Unity. So let's say we have this player, and we handle the movement of the player, and we have this simple code here. But we can restructure that to split the concerns. And again, we define a direction. So, this says we can move left and right. Then we define a function, movement direction, which basically takes in the pressed key and returns an optional direction, because we might press A, in this case A or D, but we might have different key bindings. We might also handle arrows and such, and that will produce the same direction. So maybe WASD is the one control scheme and the arrows is the other control scheme. Then when we have that direction, we can transform that into the vector that we were going to apply. So, you just do a simple switch statement here, and you say if we have the left direction, that's the left vector, etc., etc. And then there comes the impure part of the code, which is, we say, let's get if the key is pressed. This should be input. Yeah, this should be input. But basically you give it a key code and then it returns some key code if that key is pressed and none if that key is not pressed. And then we say, so what's the pressed key? Maybe it's A. And if not, maybe it's D. And then once we have that, we can say, if we have a key, let's turn that into direction and then turn that direction into a vector. And then if we actually have this direction, only then we can apply it and do the effect of changing the position. So even though it looks like a lot more code than the original one, all of that code is very simple, very reusable and testable code. And when you're working in a bigger projects, this helps out in the long run to understand the code and to prevent everything from becoming one big mess and one huge method that does everything. So thanks for your time and see you in another video.